Hi children, welcome to another video. In this video, we are going to discuss a couple of questions with the beautiful content and the way the question is presented. Okay, fine. Welcome. Let's start the discussion. We have the first question based on the structure of diborane. Structure of diborane. That is the first question leading to option A. We want to know the correct statement. Okay, option A, boron is sp3 hybridized. Yes, boron is sp3 hybridized, and this is the structure of diborane. All of you may be aware of. Here we have boron and 4 terminal hydrogen atoms like this, and 2 bridging hydrogen like this, one to top and one to bottom. So here you have a hydrogen and here you have a hydrogen, right? And overall boron makes sp3 hybridization. It makes sp3 hybridization and it is a non-planar system. It's a non-planar system. 4 hydrogen in the planar region and 2 hydrogen each, which is bridging, one above the plane and one below the plane. Option A is correct statement. Each boron has 2 set of BHB bonds. Correct? That's a bridging bond, BHB bond, which is also called a 3 center 2 electron bond. This is 3 center 2 electron bond, electron deficit bond, right? While this is a normal bond. This is normally 2 center 2 electron bond. And you can very well understand the valence electron, boron having 3 valence electron, 2 boron will have 6 valence electron. And there is 6 hydrogen. 6 hydrogen, 1 electron, and 6 hydrogen, 6 electron, and 6 plus 6. There are 12 electrons available. And how those 12 electrons are there in the diborane, all of you may be aware of. This is 2 electron, and this is 2 electron, and this is 2 electron, and this is 2 electron. 8 electrons gone. And here we have this bridging characterized by 2 electron. That is what called the 3 center 2 electron bond. 3 center means atomic center 1, 2, 3. 3 center connected by 2 electrons. Similarly here, 3 center connected by 2 electrons. So this is 3 center 2 electron bond. This is also 3 center 2 electron bond. That's a bridging bond, right? Boron lacks octet in diborane, correct? There is no octet because it is electron deficit molecule. Fine. Last one, in B2H6, HBH bond angle is different from HBB bond angle, where HB represent bridging hydrogen. So HB, HB. So this is HB, HB. This angle and this angle are different. Exactly, they should be different. Here, in fact, it is a longer bond. The bridging bond is longer bond. When there is a longer bond, bond angle will decrease. So this bond angle will be this bond angle X and this bond angle Y. Y will be greater than X. X, if it is coming in the range of some 90 degree, Y will be 120 range, right? And that is influenced by the bond length also, because the bridging bond will be more elongated, and when the bond length is greater, bond angle will decrease, right? That is also a true statement. That is regarding the structural features of diborane, right? It is sp3 hybridized. In fact, boron having sp3 hybridization, one sp3 orbital like this, one like this, one like this, while one orbital is vacant. Here you have 1 electron, here you have 1 electron, here you have 1 electron. This lacks electron because boron having only 3 valence electron. And now you can see the next boron, what happens is, next boron available here, that is also sp3 hybridized. 1 orbital like this, 1 orbital like this, and 1 orbital like this, and the orbital without electron will be merging here. And here you have one electron, here you have one electron, and here you have one electron. So the vacant orbital of this boron merges with the electron filled orbital of this boron. Similarly, vacant orbital of this boron will merge with the electron filled orbital of this boron, and they make a merging. And here actually the hydrogen comes and binding. Here actually the hydrogen comes and binding. You see that? Here comes one hydrogen with one electron. Here comes next hydrogen with one electron. Here comes next hydrogen with one electron. Here also one hydrogen with one electron. While here we have a hydrogen coming with one electron, which is there in the electron cloud. And here also hydrogen with one electron. Right? So the net result will be there is boron, boron. This bond is usual one. This bond is usual one. This is usual one, and this is usual one. While here you have an electron cloud where there is hydrogen. Here you have an electron cloud where there is hydrogen. And that's why it is called a banana bond. All of you are aware of. That's about the structural details and the concerned question based on type array. Let's go to next question. Next one. Total number of molecules or ions which have non-zero dipole moment. Non-zero dipole moment. First one, it is having zero dipole moment, and as it is square planar system, there is Cn like this, and it is square planar system, mu is equal to 0. This is also Cn, it will be Cn like this, and here Cn like this, and the dipole moment is 0 as it is mutually cancelled. While here the dipole moment is not 0. Here the dipole moment is not 0 as SH is coming like this. SH, it is coming like this, and there are two lone pairs like this. The SH will make a bend character, both the top and bottom. Both the top and bottom, it will be SH like this, bend character. So the dipole moment is non-zero value. Phenol, of course, quinol, that is also dipole moment is not 0 because they two are identical. You can see this OH will be coming OH like this, OH like that. It will carry a bend character. The lone pair of electron in oxygen make the system having a reasonably good dipole moment. Quinol is not having a 0 dipole moment, and of course this also. While this chlorine and chlorine will mutually cancel, dipole moment is equal to 0. So this is not the answer, this is not the answer, this is an answer, this is an answer. This is not the answer because it will cancel mutually. What about this? These two are transposition, they will cancel mutually, dipole moment is 0. What about here? As the way it is given, it seems like transposition, but you can see it will make a dipole moment a non-zero value, because the system is available like this. You see the system is available like this. The two parts of the carbon are available in different plane. The two parts of the carbon are available in different plane like this. It's available in two different plane. And naturally they maintain a different character. You can see the carbon available here with say hydrogen here and chlorine here, and that makes a double bond with a carbon here, and that makes a double bond with a carbon here, and here you have chlorine and hydrogen. You can see the two chlorine are not transposition. One chlorine is in the vertical plane and the other chlorine is in the horizontal plane. So they are basically available like not like this. It's like this. It's like this. See, if this chlorine is in the vertical plane, this chlorine is in the horizontal plane. Right? Why so? Because each carbon-carbon multiple bond so formed, it will change the plane. So if carbon-carbon double bond, one is in this plane, the next carbon-carbon double bond will be in the horizontal plane, and the next will be in the vertical plane, so on. Why? Because this carbon makes sp hybridization. sp hybridization, and there you have two sigma bond. What about the pi bond? This is pi bond 1 and this is pi bond 2. So the carbon making sp hybridization, this carbon making sp hybridization, go for a sigma bond left and right, and you have a pi bond 1 here and pi bond 2 here, and here px and py orbitals are free, while pz orbital involved in hybridization. Now px and py will go for the pi bond formation. Imagine px is making here, then py will be making here. That means they are in two different planes. So if one pi bond is formed along the xy plane, the other will be on the other plane, vertical plane. So naturally, carbon-carbon double bond, if one comes like this, the next will be like this. And the next will be like this, so on. So in fact, these two chlorine are not in the trans position so that they get cancelled. And that is the sole reason why allene derivatives are, this is called allene derivatives are many times for performing chirality due to this reason. Okay, so that's about, and the answer is no, yes. So there are 3 molecules which having non-zero dipole moment, right? Next one. Consider the following reaction: sodium phosphate with ammonium molybdate and dilute nitric acid. You get a canary yellow precipitate. Test for phosphorus, qualitative determination of phosphorus, and the reactions are directly from the NCERT. Calculate the total number of atoms in 15th group element which are sp3 hybridized in compound X. Calculate the total number of atoms in 15th group element which are sp3 hybridized in the compound X, right? And hope you know this is what the reactions which straight away taken from the textbook. Test for phosphorus. Phosphorus heated with an oxidizing agent sodium peroxide. I mean organic compound containing phosphorus heated with an oxidizing agent like sodium peroxide. You get a sodium phosphate, and that is converted to S3PO4, and that reacting with ammonium molybdate, you are getting ammonium phosphomolybdate. This is X. This is X, canary yellow precipitate, ammonium phosphomolybdate. And the question is, number of atoms from 15th group having sp3 hybridization. You must understand ammonium, nitrogen is sp3 hybridized, and phosphorus sp3 hybridized. There are 2 elements from group 15 which both are sp3 hybridized. Phosphate, phosphorus is sp3 hybridized. Ammonium, nitrogen is sp3 hybridized. And the answer is nitrogen, phosphorus, not 2. It is nitrogen. There are 3 nitrogen. So it is 3 plus 1. 4 is the answer. 3 nitrogen and 1 phosphorus. Suppose there is a small change in the question like how many elements have sp3 hybridization from group 15? The answer is 2. How many atoms? How many atoms from group 15 having sp3 hybridization per molecule? The answer is 4. 3 nitrogen atom and 1 phosphorus atom. Right? Next one. And that in fact is the last question dealt in this video. Let's go through a gaseous mixture containing equal moles of hydrogen, oxygen, helium. Hydrogen, oxygen, helium subjected to series of effusion steps. The composition by moles of effused mixture after 4 effusion steps. It is X, Y, Z respectively. What is X by Y? That is the question. The question is based on rate of diffusion or rate of effusion. All of you know rate of diffusion R is proportional to inversely proportional to square root of the density or inversely proportional to square root of the molar mass. So rate of diffusion is inversely proportional to square root of molar mass, right? So here it is rate of diffusion for hydrogen versus rate of diffusion for oxygen versus rate of diffusion for helium. So it will be 1 by root of molar mass of hydrogen to 1 by root of molar mass of oxygen 32, 1 by root of molar mass of helium 4. And it is subjected to 4 fusion steps. Each step, this is the ratio, and 4 times it will be raised to 4. 4 times it will be raised to 4. So what do you get? 1 by root 2 raised to 4. Root 2 raised to 4 will be, it will be 1 by 2 into 2, isn't it? 1 by 2 into 2. Root 2 square is 2, root 2 square is 2, like that. Yes, fine. So it is 1 by 32, 32. It will be 1 by 4, 4. Now we want x, 1, y. So when this is made 1, multiplied with 32, multiplied with 32, 32, multiplied with, so multiply whole with 32, 32. So this will become 1. And what about this? This will become 16 into 16, because 2 into 2, 32 into 32 by 2 into 2, 16, 16. And this will become 8, 8. So the answer is, this is x, this is x, this is y. We want x by y. So 16, 16, 8, 8. So the answer is 4. Answer is 4. 2 into 2, 4. Final answer is 4. That is yet another beautiful question based on the Graham's law of diffusion from the chapter States of Matter. That's all in this video. We will meet with another interesting questions in the next subsequent videos. Till then, take care. Bye. See you.